Okay, I'm going to get this thing started. Okay, good. I think we're ready to go here. Okay, welcome to Robot Week 2023. Each year from June the 19th, Juneteenth, to June the 24th, the Rome and H2O group at Ctest Labs does a set of presentations, workshops, sometimes demonstrations, AMAs, open to the public on regarding robot projects that we do at Ctest Labs. And so today, is one of those presentations. But before I get started on today's short talk, hopefully a short talk, I want to thank the Rome group and the H2O group at Ctest for sponsoring today's talk. Also want to give a shout out to the folks at the Northeast Ohio ACM that are participating and working diligently on the CSI Clue Challenge, and to our friends at the Oak Hill Robotics Makerspace, and to the Retro Underground Roboticists group that we work with, that we're also working with on this project. So it's a shout out to all you folks, and thanks to tuning into today's talk. Ordinarily, these talks are hardware oriented, and we tend to talk about sensors or actuators or microcontrollers or some kind of wiring or some specific hardware related issue, and we try to make that stuff easily and accessible to the public during Robot Week. But this year we thought we would do something a little different and decide to talk about, or at least give a high-level overview of the software architecture our robots have. A lot of times there's a lot of focus put on hardware and what the hardware is doing, and it's not always clear how the robots are actually programmed and what kind of software is behind these. And so today we thought we would shed at least a little light and provide a glimpse or a window at a very high level of the software architecture that we are using for some of our robot projects at Ctest Labs. In particular, we're going to present a 50,000 foot view of the robot software architecture that we're using for our robot designs for our CSI Clue Robotics Challenge. For those of you that are following the CSI Clue Robotics Challenge, it's been a multi-year effort, to say the least. This autonomous robot programming thing is hard. Okay, don't let anyone tell you otherwise. The CSI Clue Robotics Challenge features robots that use chemical forensics, let's see how do I pronounce that? They do chemical forensics and reasoning by analogy. I guess that's what the word I'm going for. Reasoning by analogy to solve what you would normally call like mysteries, and they do this while playing a game similar to the Clue game, where someone has to figure out who did it and how they did it. In our CSI Clue Robotics Challenge, we have a team of robots doing just that, trying to figure out who did it and how they did it. And they're using forensics, chemistry in the process, and analogical reasoning to accomplish that. And so for the folks that know something about reasoning strategies, you would know that reasoning by analogy is somewhat challenging in the robot programming world, and so I'll let that speak for itself. We won't be talking a lot about artificial intelligence today. Maybe this will be the last time you even hear that term. And also a note, another note of caution. We're going to be using OLD, OLD. We'll explain that later. Programming techniques. And our caution is there's no machine or deep learning, no deep learning, no machine learning, and no large language models in our talk. No, there won't be any chat GPT or no Dolly, none of that kind of stuff. So if that's what you're looking for, that's the kind of thing that you're interested in, sorry, you won't get that here. The robot architectures that we're using currently at Ctest Labs do not take advantage of any of those technologies. No machine learning, at least not the kind that is popular at this moment. We do use inductive logic programming and abductive logic programming, but the very hot topic and popular topic of machine learning and deep learning and large language models, we don't use any of that. There are no neural networks. And like I said, we use OLD programming techniques in the robots that we are programming, the robot architectures that we use. Also, before I go on, although this is directed toward the public and it's open to the public, some of the topics that we cover, it does assume that you are familiar with robotics and you have a certain amount of knowledge with respect to programming robots. And so I try to give our IM matrix here. Beginning knowledge of object-oriented programming should get you through this talk. If you know what object-oriented programming is and the basic principles of object-oriented programming, the inheritance and polymorphism and messaging and those kind of things, you'll be okay. C++, if you have intermediate knowledge of that, and we mention that only because some of the things we show, we're only showing like a small code snippet here, but it does, kind of deal with pure abstract virtual functions and the notions of container classes that have pointers to functions and that kind of thing, and so sometimes that can be a little scary. But if you have an intermediate C++ knowledge, you'll be okay. The same with logic programming. We only talk about logic programming at a fairly introductory level, but you do need to know what it is. If you have no idea what it is, this talk would might leave you a little bewildered. We mentioned Prolog with regard to logic programming as well. That's a beginning level, introductory level material we cover. And we also mention agent programming, again, at the beginning level. So C++, might require a bit of focus from folks that know C++, and everything else is at the beginning level, but not necessarily for novices, okay? So if you have no idea what object-oriented programming is, and no idea what C++ is, or no idea what any of these things are, maybe you might want to just stay tuned to see the colors in the pictures. I don't know. This is just a warning, so that folks listening to the talk and here for the talk, be prepared for the level of material that we're covering. We try to make it as simple as we can, but some of this stuff you can only make it so simple, right? And we do our best here. And also for some background information, some resource information, we want to point your attention to the Common Logic Standard, the ISO standard 24707 from 2018. They talk about the common logic interchange format there and the conceptual graph interchange format. Those are two formats that we use in many places in our architecture for our robots. And And so if you want to be familiar with what we are talking about, and we won't get much into that today, but just in general with the robot programming that we do use common logic as more or less as an interchange format between subsystems in the robots. And so if you're following along and you're trying to build these robots or understand the robots that we're talking about in architectures, you do well, and you'll be benefited by getting a copy of this. It's a freely available document on the common logic standards. There's some deviations. It's not like we're following this thing to the T, but maybe 90%, 95% of it definitely applies to what we're doing, and so you would be one step ahead if you got a hold of this. Also, the book Introduction of Autonomous Robot Programming I referenced was written by two of the authors at Ctest Laboratories. I'm one of those authors. And so that book also gives you a little background and a foot up on some of the material that we'll be covering and in general, our approach to robots and our approach to programming robots. That book gives you a high-level view of what's going on. Okay, so that's just some background information. Okay, today's talk is titled Old Programming Techniques for Raspberry Pi and Arduino-based autonomous robots. Okay, and so that's an important point here that I bring up the scale of the robotics we're talking about here. We are not talking about these, 30, 40,000 or 100,000 or $1 million robots. That's not what we're going for. We're really talking about robot systems that can be built out of garden variety Arduinos and Raspberry Pis. In fact, most of the small robots that we're building that are part of our CSI Clue Challenge, they are running Raspberry Pi 3Bs. We haven't even gone to Raspberry Pi 4 yet, anything beyond 3B plus, and we're using the basic Arduino Unos. And just as a note on the robots, you'll see a lot of robot kits, and they'll consist of, maybe an Arduino or a Raspberry Pi, and that's good to start with. But just to let folks know that the robot systems that we build will typically consist of at least one Raspberry Pi, maybe two, and almost invariably we're going to have 4 to 5 Arduinos involved. So it's a collection of microcontrollers and microprocessors together that make up the robots that we're building. Just a note there also, we tend to have like maybe an Arduino dedicated to 1 or 2, sometimes 3 sensors. We'll have another Arduino dedicated to, servos. We might have another Arduino dedicated to motors, maybe another Arduino dedicated to just a camera subsystem. And so just to let you know, we don't have an architecture where everything is done with a single Arduino or everything is done with a single Raspberry Pi. The robots that we are building and that we're programming are autonomous robots. And in order to pull off the degree of autonomy that we're at least attempting to pull off, there is no way that we were able to figure out how to get it done with a single Raspberry Pi or a single Arduino. And so we want to restrict it at least, if we can. We're trying to keep the number of microcontrollers down. We want to be somewhere under 7. And maybe 1 at most 2 Raspberry Pi. So just so that you know, it's old programming techniques, and the robots that we're talking about, the primary hardware that we are using here are Arduinos and Raspberry Pis. And so here's where the old thing comes in, and it's old in more ways than one. First, the technologies that we are using are not the latest and greatest technologies and techniques. These are true and tried very well documented, very well supported, very well known and understood programming techniques. So they're old in that regard. And then we just had fun with the acronym OLD. Object-oriented programming. The L is for logic programming, and the D is for descriptive logics. And I think that probably object-oriented programming and logic programming are fairly commonly understood and known, and maybe descriptive logics, maybe so many people don't know what that is. But the reference and resource that we gave at the beginning of this talk, it'll get you down the road for that. And, Wikipedia will help for the public if you just want to look up and get a quick look at what descriptive logics are. But I will say that we use descriptive logics and a form of foreign clause to communicate between all of the microcontrollers and the Raspberry Pi in the user interface. So although we're using, let's say, TCP/IP or serial port communications or Bluetooth communications as the physical, method of communicating between these components, the logical language that we're using is based off of descriptive logic or common logic, some kind of common CLIF format. And so that's what that's all about. And so when we say old programming, what we mean is we're using object-oriented programming and logic programming techniques largely. And descriptive logics are used as an interchange format or protocol between our subsystems. Okay, and so let's start off real quick with just a high-level view of something we call RALPH. It's our Robot Application Library Framework. And RALPH consists of two basic components. It's first an object-oriented application framework. And I want to emphasize, as opposed to some kind of web services framework or some other kind of framework, this really takes heavy usage of object-oriented techniques such as inheritance, and polymorphism plays a very big part of what we're doing, what's called horizontal polymorphism. Vertical polymorphism is a big deal, and it helps us accomplish what we're trying to accomplish. And the other aspect of RALPH is a class library. It's an object-oriented class library. Some things that aren't necessarily a part of the robot application framework, but that framework depends on, various math libraries, communication libraries, physics libraries, chemistry libraries, utilities of all kinds, unit conversion utilities, those kinds of things. And so we have a robot class library that really encapsulate a lot of the day-to-day kinds of functions and data structures and algorithms that a robot might use. We've been able to get that into a nice class library with all based on an object model. And then we have the robot our SoftBot framework that encapsulates the concept of our robot. So I want to say that this framework, if you can imagine the hardware of a robot, let's say, if a robot has wheels, we have a soft bot version of that. If a robot has a robot arm, we have a soft bot version of the robot arm. If the robot has, physical sensors, we have a soft bot version of the physical sensors. So in essence, the SoftBot framework is the software model for every single component and aspect of the hardware robot. It's the soul of the robot, so to speak. And so we have a physical robot that we build, and then we build a software robot that maps directly to the physical robot. But that said, the software robot is going to be a superset of the physical robot, meaning that there is more going on in the softbot than there is going on in the hardware, right? The software is dealing with everything that the hardware is dealing with, and more. Okay, but in a simple view, that framework is going to consist of a collection of robot parts, and these are all objects, and it's going to consist of a collection of robot actions, and those are all those would be function objects or methods. Okay, and here's where some of the intermediate C++ knowledge comes in. The robot actions are function objects or predicate objects, and this allows us to have collections of algorithms that we can dynamically use at runtime. Okay, and so the behavior of the robot, the tasks that the robot can perform, the work that the robot does is not hard coded into the robot. It's something that the robot determines at runtime, depending on what goal is required, and so we implement those robot actions as a container of function objects and predicate objects that the robot can choose to apply when it needs to apply. And those robot parts, everything in the robot, every kind of component in the robot is derived ultimately from a robot part. So if it's an arm, if it's a sensor, if it's a camera, if it's a motor, if it's an actuator, the base class for that is going to be the robot part. Okay, so hopefully that makes sense. And that softbot framework encapsulates the entire model of a robot. So if you could just imagine a software version of a robot in its entirety, that's what that softbot framework represents. And it's a framework because we can use it as a base class to make new robots, and you can override the actions, the robot actions, because those actions are virtual. They're based off of virtual predicate objects and virtual function objects. So it's designed to let users who have different robot builds than what we have and have different goals than our robot has, it's designed to let those individuals use that framework and specialize it for their own purposes. So that's what's going on. So our RALPH, our Robot Application Library Framework, is really two large components. One component is a application framework, and the other component is a class library. So that's what's going on with that. And overall, we talk about this old programming in connection or in conjunction with that, we have the old software agent architecture. And so our robots we use agent programming or our agent models to implement our robots. And this is a very high level view of, if you could imagine a main line in a C++ program, we have two big objects in that main line. One object is an agent object, and the other object is an object that represents the situation or the scenario. Okay? So in the same way that we have provided a software model of the robot, and we call that a softbot, that thing is an agent, okay, once it gets to the main line. And when I say main line, I mean the main function in a C++ program. And that's what we do use for our architecture. The overall architecture for our robots is, the high-level language that you probably see first is C++. And many of the methods, those robot actions, are implemented in C++, but many of those robot actions, although they have C++ wrappers, they're implemented in Prolog, answer set programming, and descriptive logics. And so the architecture or the immediate interface is all C++, but some of the methods are implemented, maybe as many as 30%, 40%. Those are implemented using descriptive logics, common logics, Prolog. Okay, just for those of you that know what that's all about. And so we have an agent object, and then what we model is the situation and the scenario that the robot is in. We believe that you can't have a robot that is ignorant of the situation or scenario that it's in. And so as much effort as we have has gone into modeling the robot, we've also modeled the situation and the scenario that robot is in. And so if the robot is doing a lab experiment, we've modeled that lab procedure, we've modeled the lab report, we've modeled the lab environment, and all of those models are going to the situation or the scenario object, okay? And when we construct that agent object, the constructor accepts a pointer to that situation, okay? So they go hand in hand, right? In order for us to do the kind of programming that we need to do at the software level, we model both the robot and software and the situation and the scenario that the robot is in. If in our design, in the world of the old programming techniques that we use, we don't have the notion of a robot that is discovering its situation or scenario. If it doesn't know what the situation or scenario is ahead of time, it can't do anything, right? So our robots rely on the fact that the situation and the scenario that is going to be performing work or performing a task, it relies on a definition, a detailed description of its scenario and its situation. And that description is going to be a class. So in this case, we have a class that represents the robot, and we call that softbot, okay? And imagine that we have a class called situation. And that situation deals with the physical environment, the chemical environment, the geometric environment, the real world. So we model that real world as much as possible. And so that gives us our old software agent architecture. And again, sorry for those of you that are looking for neural networks and those kinds of things. We're not going down that road. We do, however, have a knowledge base for our robots. And that knowledge base consists of a priori knowledge, definitional knowledge of lots of things, knowledge of navigation, all the trigonometry necessarily, knowledge of physics, the kind of knowledge that's involved in force and picking up things and contact and collision, it has that kind of knowledge. It uses a hybrid Blackboard inference engine. And so imagine the inference engines from expert systems or knowledge-based systems smashed together with Blackboard problem-solving methods. That's our robots have that as a form of reasoning. And so that's what goes on there. There's no deep learning or no neural networks there. These knowledge bases are designed using ontological engineering and knowledge engineering. And the best that we have and the best that we can do as far as representing knowledge in discrete structures and using epistemic algorithms. But that's for another story. So here's our architecture at the highest level. You have an agent and you have a situation. That agent interacts with that situation through sensors and through actuators. Okay, so that's what's going on. So if I were to try to explain at the highest level of what our software looks like, this would be that. We'd have a main function. That main function would declare an agent object, and it would declare a situation object. Actually, it would declare the situation first. It would instantiate and construct the situation first, and then that situation will be passed to the constructor of the agent object. Okay, again, I did say it would require intermediate C++ knowledge to get an understanding of, or at least a little understanding of what we are doing here. And here's just kind of another view. I said this was going to be about software today, but I did just kind of want to show, how the hardware fits in here. The interface that we interact with our robot, we call it roles. It's a robot situation editor. It's a piece of software that lets us enter and model the task that we want the robot to do and the environment that the robot is in. Okay, and that thing is going to run on a computer. Most of the time we have roles running on a laptop, and it can run on a laptop. Doesn't need a supercomputer or cluster or anything. At least not for this level of problems that we're having here. Roles does have the ability to talk to our Pantheon when our internal cluster at Ctest Labs when it needs to. But for the CSI Clue, everything that it needs, it can run on a local laptop. And so Rose connects to and talks to the Raspberry Pi directly. Rose does not talk to the Arduino microcontrollers. It does talk to the Raspberry Pi, and the Raspberry Pi talks to between 3 and 7 Arduino microcontrollers, and so that's a bidirectional communication between the Arduino and the Raspberry Pi, and the Raspberry Pi and the Arduino, and then the Raspberry Pi talks to the computer. And so in a very a formal sense, this is what the robot subsystems look like. You have the situation editor, you have the Raspberry Pi, kind of the main controller, and then you have Arduino microcontrollers that typically are going to be controlling the sensor set, that is the collection of sensors, the actuators, the motors, those kinds of things. And so that's what's going on there. Occasionally, we do have, in some situations, we do have hardware sensors hanging off of the Raspberry Pi. For instance, we might have our camera, I know we're using on one of our robots a Pixie camera off of the Raspberry Pi, and I think there's an ultrasonic sensor that sometimes hangs off of that as opposed to on the Arduino. That was just a matter of the kind of processing that we wanted to do, especially when it comes to image processing. It made more sense to do it on the Raspberry Pi than on the Arduino microcontrollers. So this is like the high-level thing. And I have descriptive logics here because that's what we use to communicate between all of the subsystems. Okay, so if I'm talking between Rose and the Raspberry Pi, I'm using descriptive logic. Okay, so you would imagine that in a lot of robot communications, low-level communications, some folks choose to pass ASCII back and forth, or binary strings back and forth. We pass descriptive logics between everything, and that means, and we do this because we can capture this the communications between all of these systems and subsystems, and we can process it by itself as a standalone matter, like say inside of a Prolog or a logic program, inside of an answer set program. And so we want the actual communications between the microcontrollers and the microprocessors. We want all of those communications to be understandable, human understandable. We want them all to for the most part, obey, logical, first order logic kind of processing. Right, so that's what's going on. There's descriptive logic communication between Rose and the Raspberry Pi. between the Raspberry Pi and Arduinos back and forth. That's also descriptive logics. Okay, so there's the robot, the softbot architecture. It has its runtime is obviously a binary at the its static description. This actual class description is C++ code and Prolog code, and its persistent form. That's when the program is not running. That's when the robot is not running. That's when the softbot is not running. Its persistent form is common logic, represented mainly as almost simplified horn clauses. Okay, I did say there would be a little logic programming knowledge required, and so for those of you that's following this, hopefully this will be helpful to folks that are actually trying to do what we're doing here. And just as another thing, just a communications architecture to let you know, while we are using descriptive logics as the kind of the language between the subsystems, we are using very basic things like we talk to the Arduino using either serial communications, Bluetooth, or I2C programming. Between rows and Ralph, we typically use SSH and SCP, secure copy commands, and SSH to communicate back and forth between rows and the Raspberry Pi. And then once you get to the Raspberry Pi, just depending on what kind of work we need done, we have serial communications, Bluetooth communications, I2C communications. And let me just say that I have CSV here because at the end of the day, the Arduino doesn't understand descriptive logics natively, so we have to quickly convert that to something. And CSV is kind of like an intermediate language that we use to pass things around on Arduino. We don't want to have a whole marshalling and decoding process on the Arduino that has to deal with descriptive logics. So at some point we have to get the descriptive logics code down to something simpler and faster, and that takes up less space. And so CSV is that's as far as we're willing to compromise. We won't go down to hexadecimal or machine language. That's just too far. So this just gives you a high level communications architecture, what's happening. And so, like I said before, the sensors and the actuators tend to hang directly off of the Arduinos as opposed to the Raspberry Pi. For the most part, we don't have specific hardware running on there, with the exception, like I said, we will tend to run our cameras off of the Raspberry Pi because of the image processing requirements are just too much for the Arduino, at least Arduino Unos, too much for those to handle. And we have our voice module hangs off of the Raspberry Pi. Yes, our robot does talk, but it doesn't do Chat GPT. It has something a little different. I said I wasn't going to mention language model, and so I won't. In either case, here's a simple 50,000-foot view of the communications architecture, software architecture of our robots. And just to kind of give you just a logical view, Rose kind of sends horn clauses back and forth, between Ralph, and we talked about that. And if you can imagine, on the Raspberry Pi, I may have let's say I have a ultrasonic sensor object, or I have a magnetic sensor, or a conductivity sensor. I may have that object on the Raspberry Pi, but those objects, the physical sensor is not located on the Raspberry Pi. It's actually located on an Arduino controller somewhere. So we have two objects. We have a higher level logical object that talks to a physical model of that object. So I'll have a sensor, high level sensor object on the Raspberry Pi, and then a low level sensor object on the Arduino. And that is full C++, object-oriented work that's going on in Arduino. So this is just another note for folks out there that are doing the Arduino programming that say that the Arduino is C-like. No, Arduino is implementing a subset of C++. It's not C-like. It's a subset of C++. You can't put all of C++ in there, but it is object-oriented. And so the agents that we have, sensor agents, the actuator agents that we have, the navigation agents that we have on the Arduino, they are all fully object-oriented. And the setup and loop on the Arduino, those two main functions that we all see in almost every Arduino program, we kind of use those as object request brokers. They accept object requests from the Raspberry Pi. They then translate those requests into object requests, physical object requests on the Arduino. So that's what's going on there. Okay, it's a simplified, nothing as advanced as Corba, the common object request broker architecture. It's not that advanced. It's a simplified version, but kind of picture the setup, the Arduino setup function, and the loop function as kind of a request broker between the Raspberry Pi and the Arduino, and it basically formats, takes logical object messages, and it converts those to physical object messages, and that's what's going on there. And so at the end of the day, the physical object model may be dealing with fairly low level data structures, but by the time it gets back to the Raspberry Pi, we're back at a horn clause or a CLIF, common logic interchange format by the time it gets there. And between the Raspberry Pi and ROSE, we have fully functional logic programming structures that go back and forth between those. And notice here that we have rows, stories, spaces, and roles. And role. I don't have time to go into those architectures today, but I did mention at the beginning of this talk our book on the introduction to autonomous robot programming. You could take advantage of that resource, and it has a full breakdown of what we mean by stories and spaces and role. That would be a whole nother 2 hours trying to give a high level of that. Okay, so that's the basic architecture between those three logical pieces. We have ROSE, which represents the user interface. We have the Raspberry Pi, which is kind of like the main microprocessor, and I guess you could let it qualify as a microcontroller too. And then it kind of talks to between 3 and we want to keep it under 7. Right now it's at 5. And we're really struggling to not add more microcontrollers as our problems get more complex. But the Raspberry Pi talks back and forth to those, and that's what's going on at the software level. And we did here clearly. If we were to tell you how many lines of code we're talking for this robot, it would probably scare even more of you away. But it's a lot. I'll safely say it's over 300,000 lines of code. For this version of the SoftBot. It does some pretty nice things though. And I just want to point out a couple main components here. We have a vector of robot actions. Early in the talk, I talked about function objects and predicate objects. This is what I meant by that. So our set of task components here, our vector of robot parts, those are function objects there representing the parts that the subsystem that the robot is going to be built out of, the sensors, the cameras, and all of those kinds of things. And the robot actions are really the algorithms that the robot is capable of executing at any given point, and those are dynamically used and selected by the robot. It's based on a need type situation. So we have that going on, and then we have we're able to capture the robot parts in a subsystem structure, and each of those parts are names. But I want you to notice where we have a pointer to the situation here. This hopefully is highlighting the fact that in order for this SoftBot to really function, it needs access to its situation in the scenario that it's going to be in. Another way of saying that, it needs a model of the context that it's going to perform in. If it doesn't have that model, if it doesn't know what the situation is, if it doesn't know what the scenario is, we're not going to go very far. And that situation is passed in as the constructor. And then the execute method, I kind of highlighted that here because that is used throughout all of the robot parts and robot actions. That's one of those pure abstract virtual methods that allow us to execute things from using a polymorphic point of view. So virtually every kind of class in our architecture here in our framework has an execute method. And so for those of you that are actually trying to accomplish this, and you would know what I'm talking about as far as what you would run into, the way we accomplish this is through an execute method. This is kind of like just a high-level view. I know our talk has gone over what it was supposed to go over. I tried to give a high-level view and cover some of the things that might answer some of the questions that we received over this last year, actually, with regard to our CSI Clue challenge. And so hopefully some of this will get you started. Look at the resources that we talked at the beginning, and we also have a number of videos. We post them after we do Robot Week here. We'll put them on YouTube or Facebook, so you'll be able to access them somewhere. I'm going to supply some links to some of those videos where we go into a little detail about the various architectures and programming the hardware and how we set up the code and some of the things we're doing with the CSI Clue challenge, the things that are available to the public. We make those things available to the public. And so thanks for sticking around for this talk. And this is Cameron Hughes, a software epistemologist for Ctest Labs, and enjoy the rest of Robot Week.